After age of 35, some of you are already experiencing a form of cellular energy failure, and you will not name it for another decade. You will call it burnout, you will call it hormones, you will call it stress. But the biology is more specific than that. Not because your lifestyle is broken, not because you are doing something wrong, but because the organelles responsible for generating every single unit of energy in your body have entered a phase of accelerated structural decline. And the system that was supposed to protect them has gone quiet. That organelle is the mitochondrion. And what is happening inside it right now, in your cells, in your muscle tissue, in your brain, is the subject of some of the most urgent research in longevity science today. Let me give you the numbers first. A study published in Integrative Medicine Research confirmed that between the ages of 30 and 70, skeletal muscle mitochondrial function declines by 25 to 30%. That is not a lifestyle statistic. That is not a structural statistic. It describes a change in the physical architecture of your cells, regardless of how well you eat, how much you sleep, or how often you exercise. And here is what is rarely discussed in mainstream health content. The decline is not one uniform event. It is a system failure across multiple distinct mitochondrial phenotypes, each located in different tissues, each with a different metabolic function. And understanding the difference between them is now considered one of the most important frameworks in the science of healthy aging. Let me walk you through them. The first phenotype, white adipose mitochondria. These live inside white fat tissue, the visceral fat that accumulates around the abdomen after the age of 40. These mitochondria are structurally sparse. They have minimal cristae, the internal membrane folds where ATP is manufactured. The function is not energy production. It is energy storage. When this tissue expands, these mitochondria proliferate and they become drivers of chronic low-grade inflammation. This is metabolically dangerous architecture. The second phenotype, brown adipose mitochondria, found in the interscapular region, the area behind your neck and upper back. These are metabolically active, densely packed with cristae, and programmed to generate heat through a protein called UCP1 rather than to store energy. Research from NIH confirms that brown adipose volume decreased significantly with age, particularly after age of 35. These loss directly correlate with reduced thermogenesis, worsening insulin sensitivity, and accelerated weight gain around the midline. The third phenotype, beige mitochondria. These are transitional. They emerge with white adipose tissue in response of specific stimuli, cold exposure, sustained aerobic exercise, and certain phytochemicals. When activated, beige mitochondria behave like brown mitochondria. They burn, scientific term of thermogenetic browning. And this process, unlike the brown adipose decline, can be deliberately induced through lifestyle changes. The fourth phenotype, gray matter mitochondria. This is the most clinically urgent category for professionals in midlife. A landmark human brain mapping study published in 2024 confirmed that mitochondrial respiratory capacity varies dramatically across brain regions, driven by both neural cell type and metabolic demand. Gray matter mitochondria show significantly higher oxidative capacity than white matter equivalents. What this means in practice: the cognitive deceleration the brain fog, the loss of processing speed that many adults begin experiencing in their late 30s and 40s. This is in significant part a mitochondrial event, not only hormonal, not only sleep-related, cellular. Stay with me because the next part is where the science becomes something you can actually use. There are three molecular mechanisms in the center of mitochondrial aging. You need to know each one. The first, NAD+, nicotinamide adenine dinucleotide. Your mitochondria require it to drive the electron transport chain, the biomedical process through which ATP is produced. A study published in Nature in June 2025 confirmed that NAD+ levels decline progressively with age, and that this decline directly accelerates mitochondrial dysfunction, sarcopenia, and cognitive deterioration. After the age of 40, NAD+ bioavailability can drop by more than 50%. The second, AMPK, adenosine monophosphate activated protein kinase. This is your cellular energy sensor. When AMPK activates, it initiates mitochondrial biogenesis, the creation of new mitochondria to replace damaged ones. Chronic inflammation, excess caloric intake, and sedentary behavior suppress AMPK, all three of which become statistically more common after 35 without deliberate counter-protocol. The third, PGC1 alpha, the master regulator of mitochondrial biogenesis. Aerobic exercise activates it. Cold activates it. Intermittent fasting activates it. And chronic physiological stress, the kind that operates a background noise in modern professional life, suppresses it chronically. The body does not distinguish between work stress and biological threat. The cellular response is the same. Now, let me tell you about the science that was theoretically 5 years ago and is now in human clinical trials. A prospective paper published in Nature Communication in July 2025 confirmed the therapeutic viability of mitochondrial transfer and transplantation, abbreviated MTT. The principle is direct. Isolate healthy, functional mitochondria from intact cells and introduce them into damaged or dysfunctional recipient cells. In preclinical studies, transplanted mitochondria successfully integrated into target cells. They restored ATP production, they reduced oxidative stress markers, and they reversed measurable indicators of cellular aging. The current clinical trial registry includes active human trials using autologous mitochondrial transplantation, mitochondria harvested from your own healthy tissue and reintroduced into compromised sites. Therapeutic target now includes cardiac tissue repair, neurodegeneration, and significantly for women over 35, oocyte quality restoration in fertility medicine. The obstacles remain: immune recognition of transplanted organelles, delivery precision, scalability, but the trajectory is no longer speculative. This is present tense clinical science. What we can do now, the evidence-based protocol. While that science continues to develop, here is what the evidence supports today without a prescription, without a laboratory. Zone 2 aerobic exercise, sustained cardiovascular effort at 60 to 70% of your maximum heart rate, is the most validated lifestyle intervention for mitochondrial biogenesis in middle life adults. The minimum effective dose in peer-reviewed literature, 150 minutes per week. This activates AMPK, stimulates PGC1 alpha, and increases mitochondrial density in skeletal muscles. Cold exposure, immersion, or contrast hydrotherapy activates the thermogenetic browning of white fat and stimulates AMPK signaling. Evidence-based protocols begin at 11 minutes of cumulative weekly cold exposure at 11 to 15 degrees Celsius. Time-restricted feeding, specifically a 14 to 16-hour overnight fast, elevates NAD+ viability and activates autophagy, the cellular clearance process that removes damaged mitochondria before they trigger inflammatory cascades. This is not about caloric restriction, it is about timing architecture. And there is one emerging compound worth understanding: MOTSC, a mitochondrial delivered peptide discovered at USK and Harvard. It activates AMPK, improves insulin sensitivity, and enhances mitochondrial stress resilience. A clinical trial for improving insulin sensitivity in adults with prediabetes is now registered. It is not FDA approved yet, but the peer-reviewed signal is significant enough to track. Here is the uncomfortable truth: the fatigue you are normalizing, the cognitive friction, the metabolic resistance you are experiencing in your body, that is doing exactly what biology designed it to do after age of 35. These are not personal failures. They are engineering problems. And the science is now close enough to solving them that your decision in the next 5 years will determine whether you arrive at 60 with biological capacity or already running on reserves. Your mitochondria are not failing you. They are waiting for the right signal. I will see you in my next lecture.